Thanks, Brian. I like that. I like the horse part at the end. That was my favorite. I even wrote that down when he told me about that earlier this week. If you saw my presentation in one of the earlier sessions on Monday, I apologize, some of it's the same, but there is some new stuff that I think maybe help you think about things differently, or maybe just seeing it again helps refresh your memory. So I'm going to take you a little bit on my personal journey on how we've leveraged data analytics, and really now we're focusing on scaling. And so we have this Project AI, which is our global initiative across Albemarle. And so we call that Albemarle Intelligence. And there's lots of definitions of what AI is, and I'm going to go into a little bit of that later on in the presentation. But really talk about how we have started on this and scaling from just doing basic statistical process control into leveraging that into doing machine learning. So this is the problem that we kind of set out to solve. And so when I started on this, we had a process supervisor that would wake up at 3 a.m. and get to the plant at 5 a.m. and pull up these two charts. And so what he's trying to do is he would spend 2 hours looking at this data and trying to contextualize it in his head and make some sense of it and basically say, okay, our process ran like this on the left and I got these analytical results on the right. And so he's painting this picture. But it's not just this one process, it's lots of them. So he might pull up this chart and he says, okay, I see this is a batch system. And I see maybe the green bar is wider in the center than the other green bars, and the yellow is maybe a little bit more squiggly in this batch than it is on the other batches. And he's jotting all these down on a notepad. And he's going one by one through our processes, different chemicals, different systems, different people, and he's jotting all these notes down that he's just trying to notice all the nuances in the data. And he spends 2 hours doing this. And he's been doing this for 10 years, every morning at 5 a.m., until 7 a.m. until we prepare for a meeting. And it keeps going, and these are just half of the ones that he goes through. And so this is the problem that we're trying to solve. When we give people data and all these tools, it's the same thing with the horse example, right? You're leading them to water, what are they thinking about this? And so what we wanted to do is eliminate that. And our approach was using data analytics, and we call it Pac-Man statistics. And so taking something complicated, right, and trying to take all that stuff that he's writing down and noticing and simplifying it into either it's Pac-Man or it's not Pac-Man. It's right or wrong. We're either going to do something about it or we're not. And that's all it is. And so to drive there, though, where do we start? And we started, right, with these statistical process control dashboards, and, very quickly we were able to scale this. And you might be saying, hey, we've been doing SPC for decades in your unit. And personally, as an operations engineer, I used to start out and I would print off these 11 by 17 blank sheets of paper and give it to the operators to pencil in, these run charts. And one day I saw the operator, penciling in and saw this trend up, and I asked him, well, what are you doing about that? And he says, well, I just pencil in the data points, right? It's your job to make the decision. And so this was our way of solving that, is automating all that work, but then really pushing it to the shop floor, right? Giving them the opportunity to solve these problems and telling them that, hey, there's an issue, right? And it's a real issue, and you have the ability to do something about it. So very quickly, you can kind of guess when we turned the tool on, we drove lots of improvement. These are our quality data, and that's really where we started out. That was the problem that we tried to solve, is improving quality. And so lots of different processes, different chemicals. We went 18 straight months with 0 out-of-spec product, $650,000 in savings. We used a lot of Six Sigma principles with this data analytics to drive those improvements. Completely different chemistry, completely different process, completely different unit, different people, another pilot, $1 million risk mitigation, and we saw lots of other success I could show you. But really, once we found these pockets, it's now we're in this struggle of, okay, how do we scale it, right? And so this is what we've kind of framed. And this is a little bit kind of what Brian talked about with his roadmap, and this is just the pyramid structure of it. So the goal is AI for us, Albemarle Intelligence, and how do we get there? So when we're starting off, you're talking about this data pieces, right? And we all have been talking about data. Lots of different types, sensors, instruments, operator rounds, manual data. But there's a lot of context that we're missing. And so I'll give an example. One time I was trying to tune this control valve, and I'm adjusting the proportional gain, adjusting the integral gain. It's just not responding. And so I actually go out into the field, and this control valve is has a positioner. It receives electrical signal, has a linkage arm that ties to a mechanical valve, right? And I found that there was a bungee cord tied from the linkage arm to the nearby post. So apparently an operator had seen maybe the same signal that I saw, probably not in the data, maybe in the field. He saw it was swinging, or he couldn't keep the temperature control right where he wanted it. So he said, well, I'm going to dampen the signal, right? Let me go to my toolbox. So he goes into the maintenance shop and he opens up and he says, channel locks, duct tape, maybe WD-40. Bungee cord, okay, that's going to solve my problem. And that's the tools that we're empowering our employees with, right, for this digital transformation. And so really when you started to think about these data opportunities, it's just over time we're tackling one by one. We're on this small, massive journey to restructure how we treat data and start treating it like a strategic asset instead of just another burden. So then that moves us up the ladder, right, on data organization. How are we organizing this data to prepare it for the analytics, right? How do you take something like that control valve and then do something with it? And so we have an enterprise agreement with OSI Soft, and we're leveraging their asset framework platform to be able to do that. And sometimes we're doing that already in Excel, or you might be using SQL or something. Lots of different ways of doing it, but this is an example from a zoomed-in version of one of the screens I showed you earlier of how we're organizing our data. So really what we did is we asked that process supervisor in the morning at 5 a.m., what are you looking at when you're interpreting all this? What are you jotting down? And so you might say, oh, this yellow peak here is super valuable. It tells me something about my raw materials. Or maybe this green value or this pink ramp up, is super important. And he started pointing out all these things, and we talked to other operators and getting the people involved, right? And they would say, these are the things that I'm monitoring, right? And this is just one example, and we're talking about, we talked to them about lots of other opportunities, but how do you take this and transform it into something structured, right? And when you talk about machine learning, it's all about getting the right data set. Talk to any data scientist, and they spend 80% of their time doing this, right? And then 20% or less in the analytics. So how can we automate that? Cut out that 80%. How do we analyze our data and our systems and prep them for the analytics? So then that moved us up to, okay, what's the first thing that we can really scale on analytics? And there's lots of different analytical opportunities, things you can do, but we found a lot of value in the statistics and just basic statistical process control, quality control, and our partner with that has been Northwest Analytics, and we found extreme value because it's so simple, but we just haven't been doing it correctly. So we'll go through a little exercise. I want everybody in the room to look around and find as many things as you can in the room that are brown. So go ahead, look around. Brown, look for brown. Are you seeing it? Try to get as much as you can. Okay, everybody close your eyes. Close your eyes. All right, on the count of 3, I want everybody out loud to shout out in the room as much of the things they saw that was red. 1, 2, 3. All right, open your eyes. Look for red. Where do you see red? You got the girl back there with the red shirt and the guy with the red shirt in the back. But you kind of get where I'm going with this, right? This is how we are analyzing our plants. Is you might have that guy that is, on this batch process, he's seen a problem before 10 years ago, and so what he's doing when he's looking at this is he's looking for that same thing that he saw in the past, right? He saw brown, and he's looking for brown, but the problem is what if there's something red out there that we're missing? So here in this example, which I showed you in the charts earlier, you might look and he might notice that, okay, you got some big gap in this data in the center. So he wrote that down. Maybe we changed a valve and shut down for maintenance. Well, if you peel back the layers, maybe you see some more nuance, and you peel it back even further, and although you probably can't see it, there's a super dark red faint trend line in the back. Anybody see it? Just very softly. Okay, some engineer decided to do it that color, right? Nobody pays attention for that because it hasn't been a big issue, but there is a huge signal here that was missed. And what we showed to our team was this, right? And so it's taking something complicated and putting it in the forefront and saying, this is important now. And when you analyze this statistically, that's how different it was. So each of these data points is one single batch, and that is how that one batch compared to all the other batches. And there's actually a temperature on one of our very key processes. And I won't go into the details, but there's some safety issues with getting this temperature too high. Pretty critical for our process. And you might say, well, that's what we have DCS, interlocks for, or safety instrumented systems. Well, we had all that. So the upper spec line was our DCS interlock. We didn't hit it. So you might say, okay, that's good. But if you know the Swiss cheese model, right, of all these little things happening one by one that add up into this process safety incident, right, we're not really leveraging our process data like we do personal data. So for us, this was a near miss. And so when you think about near misses, you're thinking about hand safety, right? Personal safety, slips, trips, and falls, those types of things. But where there's a huge opportunity for process data. And we found in here this temperature control loop in the DCS had an error. And so we were able to fix that and proactively and maybe prevent one of those Swiss cheese layers, further on and preventing this and addressing these near misses. So big opportunity leveraging statistics. Then that brings us to, well, what happens when you're trying to analyze all the data, right? It's too much to handle at once. And so that's really where we started leveraging machine learning. And we're still trying to figure out how to scale this properly. But I'll give you the example and kind of frame it up a lot about, we hear this word, buzzword, machine learning. It's a little buzzwordy. And so if you're talking, what is machine learning? And this is just some of the examples and applications of where you can use machine learning, and it doesn't even talk about the different algorithms behind all of these. And so it's infinite. And the way we're focusing on this is we're working in one algorithm in unsupervised learning and one algorithm in supervised learning. That's it. And it's an element of machine learning. And then maybe eventually we start to work and add value here, but we found a lot of value. And when you hear unsupervised machine learning, what that is basically you take a bunch of data, dump it into the algorithm, or you press the go button, and it finds all these different clusters of, different ways you've performed, or maybe different groups of how the data is structured, but it has no context for really what it is. That's up to the user. Supervised learning is kind of where you're training it. I have this data, and then this should be the result. You might feed it lots of pictures of cats and dogs and say, this is a cat, this is a cat, this is a cat, this is a dog, this is a dog. The next time you show it a picture, it should know whether it's a cat or a dog. That's what supervised learning is. So our first trial was in unsupervised learning, doing principal component analysis. And what we did is we pulled 2 years of data across these 3-tier vacuum pump trains, 3 vacuum pumps in series, and they pull super deep vacuum, 32 different variables. And we put it through this model. And so what it did when we pulled all that data is it says, hey, this is a 3-dimensional representation of all those 32 variables. And we noticed that, hey, it's got 2 kind of clusters of data, saying all that data you got kind of in 2 zones. Well, we look into one of the zones and, oh, that's when the pumps are off. Well, that's real helpful. So we delete that data, rerun it when the pumps are running, and say when the pump system is on, we're running in 3 different modes. And we zoomed up in on that on a different time frame. This is 2 years of data, and the gray spots are when the pumps are off, and the brown is the model. And so one cluster was this data here, one cluster was this data, one cluster was this data. So we pull failure information, and we found we had a motor failure here and a seal failure here. So if we zoom in on the seal failure, we have a maintenance guy that goes around, takes vibration every 30 days, and then they monitor that over time. And so on July 30th, he found no vibration. August 30th, high vibration. Well, the model found it the moment that it happened and actually told us that the seal pot level went empty, and we ended up causing the pump to cavitate. And we ran like that for a long time with no knowledge. But the problem with all of these systems, when you talk about machine learning, and for us, it's, gets complicated, right? You might have to have a PhD on your team to be able to interpret that, or a huge team of people. But the real value that we found, especially with scale, is how do you push this to the operator level? How do you push this to the shop floor? Can't push something like this. What are you supposed to do with it? So the whole journey is, how do you scale this, right? How do you take something complex, put it back into, instead of either Pac-Man or not Pac-Man, it's right or wrong, we're going to do something about it or not. That's really what we want. And so the operator now can click this alarm, and it pulls up this chart. And this is a T-squared chart. I won't go into what that means, but basically each of these data points is a summary of all the 32 variables. And they can, when it goes out of range, they can click on it. It gives them a contribution of which variables are causing the variation. What should I investigate? What should I look for? And that helps you look at lots of data. And then one of the new things that we're doing and kind of experimenting in, and this is on the supervised learning side, is we structured at the beginning this whole problem of painting the picture of a process did this, I got this result. And so the way we're handling this is, we talked about these data sets. And so we've been creating these data sets kind of separately. And then we're creating some aggregation features and merging to say, okay, merge all those and synchronize them together to where you have one data set with all the different information that you need on the same rows and columns. And then we're running this partially squared algorithm on that. And then it's basically saying, hey, our process did this, we got this result. And then now we can say, okay, our process is doing this, what do you think the result will be? And we push that back into the system, and then we push that back to the operator, and then we give them this chart. All this being automated. And so you pull up the chart, and this red line that's kind of tapering off at the end is the predictive analytical model. So it might be, percent aluminum or particle size. And the blue is actually the lab result. And so you can use this to maybe verify the model. If the blue and red are drifting apart, maybe you need to retrain the model, or maybe something's wrong with your lab data or something. But this allows you to start reacting sooner, predicting and saying our process is doing this. Okay, this is going to be the result. I need to turn this knob right now. And so this is how we're approaching this. And then that moves us into AI. What is AI? Lots of buzzwords. And this is kind of how I like to think about it. And this is one of my favorite memes. Just kind of tacking on lots of different buzzwords on, the same stuff. But I had to look it up in Webster. So what does Webster say? AI is a branch of computer science dealing with simulation of intelligent behavior in computers. It is the capability of a machine to imitate intelligent human behavior. Now, in one of the earlier sessions, one of the guys was asking the question, well, this whole digital transformation thing, isn't that just a relabeling of things that we've already done? Kind of yes, and kind of no. But the value that we found is think about AI maybe in this, and they call it the AI effect. What is AI? Well, it's anything that computers have not already done. And then Rodney Brooks, went too far. Rodney Brooks said, every time we figure out a piece of it, it stops being magical. We say it's just computation. And it's really true. So think about the Roomba, right? It, I think, came out in the early 2000s. At that time, man, that was super advanced, and everybody would have considered that AI. Now it's just like, well, that's the Roomba. And so this is my personal Roomba, and at the house we have a name for him. His name is Roger. And every morning at 5 a.m. I get a notification on my phone that Roger's stuck on the edge of a cliff. And so I come downstairs and I see Roger in this position on the carpet. And so Roger has 6 sensors on the base of the Roomba, and these sensors are supposed to detect if it's a cliff or not, but it just does it by detecting light. And so the designers didn't really consider, well, what if your rug has a lot of, carpet has a lot of dark spots in it? Well, it might think that's a cliff, and so it gets its way on this little red part and gets stuck. And this is every single morning, old Roger gets stuck somewhere, have to pick him up and re-dock him. He never docks himself. So there's a little work with the AI. It's not complete autonomous. Sometimes underneath the couch, you have to wedge it out. And then we had a guy online that I found had an unfortunate incident where, he had a Roomba and also a dog. And the dog made a mess, and then the Roomba had found it, did its normal routine, drug it around the house. And this is his drawing to kind of save you the eye burn of it. he replaced all the carpet in his house, and the Roomba company gave him a free Roomba to, replace his broken one as compensation. So you have to ask yourselves when you're talking about these systems, do you understand the whole pyramid, right? Do you understand if the data point, that control valve, that is on the temperature controller that has the bungee cord, are you going to allow that to completely automate your whole plant? And so I think you really have to see that there's pockets of where you can use this. And the way we're approaching it, right, is you have all this data, and we've organized it and run the statistical analysis to say this is wrong, right? Or we need to focus on this. And then with the machine learning, you can say, well, I'm going to summarize all this large amounts of data, and then the machine learning model is going to tell me whether it's right or wrong or good or bad and where I need to focus. And then with the machine learning, because your plants are a lot bigger and you have lots of data streams, then you can continue to leverage them to solve bigger problems across your organization. But with the real end goal of saying you can't show this to your people, right? You have to be able to summarize it. What am I going to do about it, right? Where can I focus? And so feeding back into that same kind of mindset of it's either Pac-Man or it's not, it's either right or wrong. The AI, we're either going to do something with it or we're not. So I'll leave you with this from William E. Deming. In God we trust, all others bring data. Thank you.